To start off on Chapter 4, we're going to talk about different ways of combining various kinds of functions. We start off with a more straightforward way, which is just the adding functions together, subtracting functions, multiplying and dividing functions. And this works out exactly how you might expect it to. If you wanted to add together the functions f of x and g of x, f plus g of x is just going to be f of x, the function f of x, plus the function g of x. Similarly for subtraction. So, for example, if f of x is the function 3x minus 2, and g of x is the function x squared plus 4x minus 5, then f plus g of x is just going to be f of x plus g of x, which is going to be 3x minus 2, plus x squared plus 4x minus 5. Okay, and then we might want to simplify this a little bit. And so this function f plus g of x, if we combined our like terms, we could express this as x squared plus 7x minus 7. Okay, now f minus g of x, it's the exact same idea. You can express it as f of x minus g of x. We just need to be a little bit more careful here because we're subtracting one function from another. So start off with f of x, that's your 3x minus 2. And we're going to subtract from that all of g of x. So I'm going to put g of x in parentheses here, just as a reminder that we're subtracting this entire function. Right, because it's f of x minus g of x, we need to make sure that that negative sign gets distributed into the parentheses. So I could rewrite this as 3x minus 2 minus x squared minus 4x, because the negative got distributed to the positive 4x, and negative or minus a negative 5 would be a positive 5. A negative times a negative is a positive. So this in the end is going to simplify to, we have negative x squared minus 1x. Finally we have negative 2 plus 5, so that's plus 3. So f minus g of x would be this expression here, x squared negative x squared minus x minus 3. So just be mindful of any negative signs. Let's try to, apparently you can't shrink that up a little. Alright, well f times g of x is the next one, and again, f times g of x is going to work out exactly how you'd expect. It's just f of x times g of x, so we do it underneath so that I have some space. F of x times g of x would be the function 3x minus 2 times x squared plus 4x minus 5. And if we needed to, we would distribute this out, multiply 3x times each one of these, and then multiply 2 times each one of these as well, and add your like terms. But it's not even really necessary here. Oh boy. Unless there's a reason to actually do this multiplication out, it's fine to just leave it in this factored form like this. And finally, for our last combination of functions, we have f over g of x. So this is going to be f of x over g of x. This is going to be a rational function. So we end up with f of x is on top, so that's 3x minus 2 on top, over g of x on the bottom, x squared plus 4x minus 5. Now, notice that when we add, subtracted, or multiplied two polynomial functions, the result was still a polynomial. But when you divide two polynomial functions, the result is not necessarily going to be a polynomial anymore, but it will be a rational function. Just something to be aware of. The domain could change when you're looking at a rational function. Right? The domain for a polynomial function is all real numbers. So as long as f and g are polynomials, the domain is going to be all real numbers. But for a rational function, the domain's not going to be necessarily all real numbers anymore because that denominator function g of x could be equal to 0 somewhere. So here the domain is going to be all real numbers except where the denominator, that's g of x, is equal to 0. Alright, let's look at some more examples. Actually, let's define a composition of functions. So this is our last way of combining two functions. We call it a composition, and it's denoted with this notation f little circle g. We would read that as f of g of x. f of g of x. That's how you would read that. And what that means is we want to plug the g of x function into the f of x function. So g of x is getting inserted into the f of x function. So let's try to get a sense of what that means. If f of x is a function x squared plus 3x, and g of x is a function x minus 2, we're going to try to get a sense of what f of g of x means. First of all, let's just remember what it means to evaluate a function at a particular x value. If we wanted to find f of negative 5, we would need to replace each x with 5, right? So in order to do that, what we would do is replace this x with negative 5 squared plus 3 times negative 5. So I just took that f of x function and I replaced every instance of x with a negative 5. Well, if I wanted to find f of g of x, I'm using the same idea here, except what I'm going to do is I'm going to replace every instance of x with g of x. So I'm evaluating the f of x function at g of x. In other words, I'm trying to find f of x minus 2. So what I'm going to do is I'm going to replace every instance of x up here with x minus 2, because g of x is equal to x minus 2. So that's going to give me, right, replace every instance of x with x minus 2, x minus 2 squared plus 3 times x minus 2. That's what your f of g of x is going to be equal to. And again, if you needed to, you could distribute that out and combine your like terms. But it's fine to leave this as is, unless they give you a reason not to, right? Unless there's something you need to do with this. Alright, now on the other hand, what if we wanted to find g of f of x? And again, we read this as g of f of x. So this means plug the f of x function into g, right? So I could rewrite this, so I'm plugging f of x into there. So I want x squared plus 3x to get plugged into the g function. So that means I'm going to write my g of x function, but I'm going to replace each x with the f of x function, which is x squared plus 3x. Alright, so take your g of x function now, that's your x minus 2, and replace each x with x squared plus 3x. Well, that just means I'm going to have x squared plus 3x minus 2. I just replaced that single x value in the g of x function with x squared plus 3x. Right, so g of f of x is equal to this, x squared plus 3x minus 2. So you can see that in general, g of f of x is not going to be equal to f of g of x. Let's do some examples. Let's say f of x is a function x over x plus 2, and g of x is a function x cubed. So we're going to start off by finding f of g of x, right? Remember, this means g of x getting plugged into the f of x function, which means f of x cubed. So we'll take the f function and replace every instance of x with x cubed. So when I replace every x with x cubed, I'll get x cubed over x cubed plus 2. Alright, now what about g of f? This is a reverse, so this time I'm plugging f of x into the g function, which means in the g function I'm going to replace every x value with f of x, which is x over x plus 2. So now you're going to look at the g function over here and replace every instance of x, that's just this x cubed part here, with x over x plus 2. So I've replaced my x in the g of x function with x over x plus 2, and I get this rational function raised to the third power. Alright, let's do f of g of 1 here. Alright, well there's sort of two different ways to do this. One thing we could do is, we already know that the f of g of x function is equal to x cubed over x cubed plus 2. We found that in problem 1. So I can just evaluate this function at 1. So this would be 1 cubed over 1 cubed plus 2. That's 1 over 1 plus 2. That's 1/3. Now another way that we could have done this is we could have also found g of 1, and then plugged that into the f function. Alright, so g of 1 would be evaluating the g function at 1. Well, g of 1 would just be 1 cubed, which is 1. And plugging that into the f function gives you 1 cubed over 1 plus 2. That is 1/3 again. Okay, so you get the same thing both ways. It's just two different ways to do it, but you should end up with the same result. Now let's try g of f of 1. So again, g of f of 1, we already found it here in problem 2, is equal to this function right here. So I can evaluate this function at 1 and get 1 over 1 plus 2 raised to the 3rd power. That is 1 over 3 to the 3rd power, which we could rewrite as 1 cubed over 3 cubed, or 1 over 27. Alternately, we could have found g of f of 1. So first find f of 1, that's your innermost. F of 1 would be 1 over 1 plus 2. That's 1/3. And then plug 1/3 into the g function. So this would be 1/3 cubed. Okay, again, we get the same thing, 1 over 27. So either way you do it, you should get the same thing. Alright, now, what if we just have two graphs? We don't necessarily have the equations of those graphs, we just the equations of those functions, we just have the graphs of those functions. Well, as long as we know the definitions for how we are combining these different types of functions, we can compute different combinations of functions at specific values, right? So we knew, for example, that f plus g of x is just f of x plus g of x, right? Which means f plus g of 1 is just f of 1 plus g of 1. So I can use these graphs to figure out what this should be. Alright, f of 1 is the output of the function when x is equal to 1. Alright, well at 1, we have a point on the graph at 1, 1 here. And g of 1, let's see, we have a point at 1, 3. So f of 1 is equal to 1, and g of 1 is equal to 3. So f of 1 plus g of 1 should give you an output of 4. Alright, let's try the next one, f minus g of 1. Again, we can think of this as f of 1 minus g of 1. We already saw that f of 1 was 1 and g of 1 was 3. So f minus g of 1 should be 1 minus 3, or negative 2. Alright, what about multiplication? Again, f times g of 1 is just f of 1 times g of 1. So that's going to be 1 times 3, or 3. And f over g of 1 should just be f of 1 over g of 1. So that should be 1 over 3, or 1/3. Alright, now, when we get to the compositions of functions, things get a little more interesting. You have to start thinking a little bit more clearly here. So f of g of 1 means g of 1 plugged into the f of 1 function. Now I know that g of 1 is equal to 3, right, because we found that up here. G of 1 is equal to 3. So this is like saying evaluate the function f at 3. In other words, plug 3 into the f function. Alright, let's go back to the f graph. When x is equal to 3 here, the output of the function is here at 1. Okay, well, we get 1 again. That's sort of a fun surprise. Right, we happen to get an output of 1, but we had to actually plug that g of 1 value into the f function. Now let's try to do it backwards now. Let's try to do g of f of 1. That means find f of 1 and plug it into the g function. Alright, f of 1 is equal to 1, so this is the same as just finding g of 1. Oh, okay, we already found that that was equal to 3. Great. Alright, now finally let's try to find f of g of 4. Right, so just like before, this means f of g of 4, so plug g of 4 into the f function. So I need to find g of 4. Let's go to the g graph. G of 4, okay, we have a point here at 4, 0, so the output there is 0, which means I'm going to replace this g of 4 with 0. Now I need to evaluate the f function at 0. So go to the f function. If you plug this function, if you evaluate this function at 0, you have this point at 0, 2. We have a y value, an output of 2. So we're going to use this idea of finding different combinations of functions, but especially compositions of functions, to help us as we start learning about one-to-one functions in the next section.